Chapter 9 and 10, Heat and Thermodynamics. So the molecules in any form of matter are moving, and all molecules have a certain amount of kinetic energy. So kinetic energy is the energy of motion. And we're going to see that there's a direct correlation between temperature and kinetic energy. So the absolute temperature of an ideal gas and the average kinetic energy are directly related. So if I increase the temperature, I'm going to increase the kinetic energy, and vice versa if I decrease it. So if one is doubled, the other one is doubled, and we can see that when we look also at, when we think about kinetic energy. So as the particles are moving around, if we were to look at a picture of the particles, we would see that as we add heat, the molecules are going to move around more. As they move around, they're going to spread apart, and there's going to be more space in between them. So we see that as we add heat, that they expand. So we're going to be talking about the different states of matter: solid, liquids, and gases. So what do we use to measure temperature? So temperature is a measure of the average kinetic energy. So that's why these are directly related of the molecules in a material. We know temperature is a scalar quantity. It doesn't have direction. And we use thermometers to measure temperature. So a long time ago when I was little, we always used mercury thermometers. Okay? But the mercury thermometers were glass, and if they broke, the mercury, spilled. And what they realized after that, because when I was little we used to actually play with the mercury in our hands, they realized that mercury is absorbed through your skin and it can be dangerous. So they no longer use mercury in thermometers that you would use at home to measure your temperature, or that we use here in school and things like that. So again, it's a tool to measure temperature. Now, a degree is the unit of temperature. There's different scales that we use, and the Fahrenheit scale is what we're used to at home. So, when you're sick and your, parents, when you were little, took your temperature, and that we said that normal body temperature is 98.6, the Fahrenheit scale is what we're used to using in everyday life. But that's not the same scale that we use in the classroom and for other applications. So the Fahrenheit scale, water freezes at 32 degrees, and it boils at 212 degrees. The Celsius scale, water freezes at 0, and it boils at 100. So a change in 1 degree Celsius is bigger than a change in 1 degree Fahrenheit. And then we're going to talk about the Kelvin scale, because the Kelvin is the standard scale of unit of temperature in the metric system. So if I want to convert from Celsius to Fahrenheit, the temperature in Fahrenheit is 9/5 the temperature Celsius plus 32 degrees. And then for Fahrenheit, this is what we do. For the Celsius Kelvin temperature conversion, the temperature is the temperature in Celsius plus 273.15. But the difference in the temperature is the same if I'm looking at the difference, like 1 degree difference, delta T. All right. So for most scientific work, temperature is measured on the Celsius scale, and the average body temperature is about 37 degrees. Okay. But the SI unit of temperature is Kelvin. So 0 on the Kelvin scale is the coldest possible temperature, also known as absolute zero. Have we ever reached this? No. We've come very close, but we've never reached absolute zero. So here are some important temperatures, and again, we've learned a lot of this before. So 0 and 100 for Celsius, and then we look at all the corresponding temperatures, and then absolute zero. So transfer is the basis of understanding what's meant by heat. Now, when we talk about heat, heat is a physical quantity that I can measure. Can I measure mass? Yes. Can I measure length? Yes. Can I measure heat? Yes. Can I measure cold? No. There's no such thing as measuring cold. So this morning it felt cold out, but you cannot physically measure cold. Cold is nothing to measure. Okay? It's a word that we use in everyday language to describe, but when we talk about measuring a physical quantity, the physical quantity we're measuring is heat. So we can talk about heat gain or heat loss, but there's no such thing as coldness to measure. So that's one of the first misconceptions we want to get out there. Okay? So an object can change its internal energy by absorbing or releasing heat energy. So heat is a form of energy. If no phase change, for example, freezing or boiling are occurring, the absorption or the release of heat energy is accompanied by a change in temperature. The only way for me to explain this to you is by looking at a graph. So we're going to be looking at a graph and completely understanding these types of temperature versus energy diagrams. Okay? So heat, the energy transferred between materials or parts of material that have different temperatures. So in order for there to be, again, when we're measuring the heat, there has to be different temperatures. So number one, heat's a form of energy. We know that heat makes molecules move faster. The direction of the heat exchange between objects depends on the relative temperatures. All right, so when we talk about heat transfer, there's three types of heat transfer. There's conduction, the transfer of energy from molecule to molecule by collisions. Okay? Convection, the transfer of energy by the flow of a liquid or a gas. And then radiation, the transfer of energy by electromagnetic waves. And we're going to look at different examples, and sometimes we'll talk about these as far as like everyday life. All right, so a conductor is a material that electrons move easily through it. And we know that metals are good conductors of heat. That's why we use them for like pots and pans when we cook and stuff like that. That's why the handles are not made out of metal. A lot of times they have insulators, which are poor conductors, like rubber and glass. Like at the end of all the tools, you always see like my grandfather's tools always had wood on the end, but wood splinter. So now every tool has what? Rubber or plastic on the end because they're an insulator. Okay. So this gives certain examples about that. It takes different amounts of heat to change the temperatures of equal masses of different substances. So each material has its own specific heat. Now, when we learned about friction, remember every single material had its own specific coefficient of friction, and it was different for every material? Well, every material has its own specific heat. Okay? So the amount of heat energy absorbed or released is directly related to three things. The substance itself, because that's its specific heat, which makes it unique, the mass of the substance, and then the temperature change. So the specific heat is, what is specific heat? It's the amount of heat needed to change the temperature of 1 gram of a substance 1 degree Celsius. Now this is in your book on 314. I cut and paste the chart from your book. So the specific heat of ice, 2.09 times 10 to the third joules per kilogram per degree Celsius. For water, it's 4.86 times 10 to the third. And then for steam, it's 2.01 times 10 to the third. Okay? If I want to calculate the amount of heat, this is the equation. So Q stands for heat. Q is equal to mc delta T. So it's equal to the mass of the substance times the specific heat capacity. Sometimes instead of C, they might call it C subscript P, times delta T. And remember, delta T is always going to be the final minus the initial temperature. So here's an example. A sheet of aluminum foil has a mass of 20 grams. At first, it's room temperature, which is about 20 degrees Celsius. You leave it in a heated oven until the temperature is 80 degrees. How much heat did it absorb? So Q is equal to mc delta T. 20 grams. Now, I don't have to convert this grams because the specific heat is joules per gram degree Celsius. So if these are the same, it's okay because they'll cancel. All right? If my heat capacity is not in joules per gram Celsius, if the units are different, I have to match it up to the mass. And then my final minus my initial temperature. And that's it. So that's the heat. So when you heat an object, it gains energy. When an object cools, it loses energy. So we're talking about energy in the form of heat. So there's obviously lots of uses for heat. You know, we use it to cook our food. Maybe some of you put the heat on in your car this morning, driving to school. A lot of times we use it to kill germs. because heat can kill germs at certain temperatures. All right, so now phase change is dependent upon the substance. So a phase change, we know that we can, like for water, if we're going from ice, which is a solid, to a liquid, which is, or to like a gas, which is like ice. Okay. So from solid to liquid, this is called melting or fusion. From liquid to solid, this is called freezing. From liquid to gas, this is called boiling or vaporization. From gas to liquid, this is condensation. From solid to gas, sublimation. And from gas to solid. We've done a lot of these in what? Middle school, right? The difference is now that we might calculate the amount of heat to do some of these temperature changes. Now, when you use something called a calorimeter, okay, a calorimeter is something kind of like an insulated cup with a cover, and those of you who took chemistry did this, and you put like a thermometer in the top. So this is calorimetry is just a procedure to measure the energy transferred from one substance to another, the heat energy. And we can calculate different things. We can calculate the amount of heat during a phase change and not during a phase change. Okay? So let me just show you something. Whoops. This isn't in the notes, but all right, let's say I want to go from ice to steam. Okay? Now, what happens is that, let's say I have ice at, I know that the change of state occurs at 0 degrees Celsius. Another change of state occurs at 100 degrees Celsius. So let's say I have ice and it is negative 15 degrees Celsius. Okay? When I want to go from negative 15 degrees Celsius to this border is a change of state. If I want to calculate the heat that it takes, I would use the equation Q is equal to mc delta T. So I would do the mass of the substance times the specific heat for ice times that change in temperature, which would be from negative 15 degrees to 0. Now, that's going to take me from here to here. Now I stop at 0 degrees Celsius, but when I stop at 0 degrees Celsius, that's the border. I want to go from ice to water, which is a liquid. Remember, this is a solid, this is a liquid, and this is a gas. In order to cross this borderline, it takes energy. So even though I'm at 0 degrees Celsius, it takes energy to change just state. In order to change this state, the energy there is going to use the equation Q is equal to mHf. So this amount of heat is equal to mass times the heat of fusion. Okay, now I'm at 0 degrees Celsius. How much heat? So just within the liquid state, I can calculate the heat. Q is equal to mc delta T. The heat would be the mass times the specific heat for water times that change in temperature. The change in temperature would be 100 degrees. Now I get to 100 degrees Celsius. I'm at the border. But it's going to take me energy to switch just from liquid to a gas, from water to steam. That takes energy too to cross that borderline. So now if I want to cross this borderline, Q is equal to mHv, so the heat is the mass times the heat of vaporization. So let's say I want to go to 120 degrees steam, then this, I'm going to have to use Q is equal to mc delta T again. I'll do the change in temperature, which would be 120 minus 100, and now I'd have to look up the specific heat for steam. So if I wanted to calculate the energy that it takes to go from negative 15 degrees Celsius, so that's like ice, to steam at 120 degrees, I'm going to have to add up 5 different values. First, it takes energy to go from negative 15 to 0. Then it takes energy to cross this borderline. Then it takes energy to travel that 100 degrees. Then it takes energy to cross the border, and then it takes energy again. So let's look back at the notes. So it says here, and I wanted to show you that visual to explain this. So reverse phase changes, melting and freezing, for example, occur at the same temperature. Therefore, the melting point and the freezing point of a substance refer to the same temperature. If the heat energy is being added to the system, melting occurs. If it's being removed, freezing occurs. During a phase change, the temperature of the substance remains constant. Remember in that equation I showed you, and I showed you again, there's no delta T. Because when I am going from ice to water at 0 degrees, am I changing temperature? No. But it takes energy to change phase. And we can look at the amount of energy and compare the amount of energy it takes to change phase within the same temperature than changing temperature within the same phase. Alright, so during a phase change, the temperature remains constant until all the substance has been converted from one phase to another. This fact means the average kinetic energy of the particles is not changing. The energy that is absorbed or is released during a phase change is associated with changes in potential energy of the molecules. Because remember when we learned conservation of energy? Alright, so during melting, a solid absorbs a specific amount of heat energy in order to be converted to a liquid. This energy, known as the heat of fusion, is sometimes called a latent. The word latent means hidden heat because its addition is not accompanied by a temperature change. Now the equation is Q always means heat, so the heat of fusion is equal to mass times the equation for the heat of fusion. So this is the energy associated with this. And then the heat of vaporization, so this is the energy, is equal to M times HV. Here is our graph. So everything we've been talking about all led up to this graph. This is a type of graph that you're going to see on any type of standardized test. But I could ask you 20 questions just on this graph. Okay? So they call this either a temperature versus energy graph or a temperature versus heat graph. So here's the graph. You're always going to have temperature here. And then here it's either going to say heat or it's going to say energy. So what we see here these are actually different states. So this happens to be water. Okay? So what happens here is the horizontal segments of the graph indicate the times when the temperature was constant. Because here, if you look at part B, this is 0 degrees Celsius. If you look at part D, this is 100 degrees Celsius. Well, we know for water, this is the temperature at which water freezes. But this could be ice or this could be water at 0 degrees Celsius. At 100 degrees Celsius, it can be either water or steam. So these horizontal lines, these represent when it's changing phase. If you remember the other one that I showed you, so this horizontal line here is here. This is the border line. Okay? Now, these other lines here, this one, and this one, these represent a change in temperature. See here the change in temperature? So if I wanted to calculate this, this would be 0 minus 25, this would be 100 minus 0, and this one, whatever this temperature is. So the slope lines show a temperature change, which can be an increase or decrease, but it stays the same. So this is a solid, this is a liquid, and this is a gas. Now, on this same type of a graph, there's so many questions they can ask you. They can ask you things about temperatures. They can ask you about, what's the boiling point. They can ask you what's the heat of fusion or what's the heat of vaporization. They can ask you to calculate the specific heat from the graph. So from this graph, if I wanted to calculate the specific heat, C, I would use my equation. Q is MC delta T. I'd rearrange the equation and say that C is equal to Q over M delta T. Then, from the graph, what I would do is I would pick 2 points to read the temperature change. Okay? So let's say here, So here I could say 100 minus 0. They would give me the mass, and then again I could look at the heat by looking at it on the graph. So there's 20 different things at least they can ask you on these types of graphs. So that's what we're going to practice doing also. And then thermodynamics is chapter 10. There's not really, I think, calculations that we need to know for that. So, I mean, the main equation is delta U is Q minus W, but we'll go over this another day, and that's it.